This is a work that we've been doing with a lot of collaborators to study how the dynamics of stars on the main sequence evolve using Kepler data. So I'll be focusing on solar-like stars and also on the magnetic activity more than rotation of stars. So just a little bit of background or context about what has been done in the past in terms of rotation-age relationships. So almost 50 years ago, Skumanich studied a couple of clusters and the sun in terms of rotation, magnetic activity, and lithium as a function of age that you can see here, the three quantities there. You can clearly see that they decay with the age of the stars. And he derived this relation between the rotation period that increases with the square root of the age of the star, which is also known as the gyrochronology relation. And basically, this is related to the angular momentum loss through magnetized stellar winds. And more recently, using Kepler data, where we had seismic ages, rotation periods, either from photometric data or from the seismology, we showed that there was weakened magnetic braking that was happening for stars during their mid-life, and showing that actually gyrochronology might not be applicable to all types of stars, where the sun might also be. So here you have the rotation period as a function of the ages, and Jen already showed this a little bit, so I will go very quickly. But basically, you can see that stars rotate faster than what was expecting from the gyrochronology classical relationships. And you can also see that the sun seems to be in this region where it's in a transition phase. So this is about rotation. Then magnetic activity also decays with the age of the stars. And Mametek and Hildebrand, for instance, studied young clusters and some field stars where they had isochronal ages for those in terms of ages of the stars as a function of the classical spectroscopic proxy of magnetic activity in R prime HK. And they derived a relation between these two quantities, R prime HK and ages, where we also have a dependence with the color of the star. There was also a recent work by Lorenzo Oliveira and collaborators, where they studied solar twins and showed that maybe activity and age relation can be valid up to 6 to 7 gigayears. Okay, so since we have all these, oops. Is it working? Yeah, okay. Since we have all these, yeah, no, okay. Since we have all this Kepler data, we can actually measure rotation periods using photometric, the modulation that we see from the spots and active regions coming in and out of sight. Rafa already talked about the different techniques that we're using, so I will not go through them, but you have time frequency analysis, autocorrelation function, and we also implemented machine learning techniques to analyze a large sample of data. And since we are measuring rotation period because of the presence of active regions on the surface of the stars, we can define a magnetic activity proxy, which we call the SPH index, which is basically the standard deviation of the light curve. So we've been using subseries of length 5 times the rotation period. So here you have the time series from Kepler, and then this SPH as a function of time. And we take 5 times the rotation period for the subseries because in order to ensure that we are measuring variability coming from the magnetic activity of the stars. And then we take the mean value of this SPH to have a global index. So we applied our pipeline on 160,000 targets observed by Kepler, main sequence and subgiants, and we got reliable rotation period for more than 55,000 stars almost doubling what was available in the literature before for Kepler. So here you have the distribution of the rotation period and the SPH as a function of the effective temperature for main sequence and subgiants. And if you look at the G stars and F stars in terms of SPH and rotation period relationship, you can see that for the G dwarfs, the faster the star rotates, the more active it is, which is what we expect. Whereas for the F dwarfs, it seems that this is not so clear. Okay, so let's move on to studying the activity using the key parameter for the random models, which is the Rossby number, which is basically a measure of which process is dominating in the star, whether it's the Coriolis force or the advection. So it's the ratio between the rotation period, which is a quantity that we are observing, and the convective turnover time, which is basically coming from models. So there are different techniques to compute this convective turnover time. Either you can use some semi-empirical relationships, like what Noyce and collaborators did in 1984, where you have a dependence on the color B minus V. More recently, with Enrico Varsaro, we also derived a new calibration using seismic models. And then you can also use models where you're fitting effective temperature, log G metallicity, and the rotation period, which is what we've been doing with Jen Van Seders and Zach Clater. And finally, you can also use the fluid Rossby number coming from 3D numerical simulations of convection for rotating stars, done, for instance, by Sasha Brun and his student. Okay, so here we decided to focus on the model Rossby number because this is the Rossby number that's applicable to most of the targets that we have. So here we focus on the main sequence stars. So we have 40,000 targets. You can see the SPH as a function of the Rossby number from the models normalized to the solar Rossby number. And basically, this is a shape that has been seen in many magnetic proxies in the past, so it's very similar. So I'll just walk you through it a little bit. So going from the young stars or young Rossby numbers, you will have this kind of saturation, which is also seen in the other proxies. Then you have the decrease that we already talked about with Skamanic from Mamajek. And there is this interesting kink or dip around here that has been seen mostly in the Kepler data. And yeah, I also wanted to mention that you can see this very nice upper envelope, but there is still some dispersion in the points here. And this is basically due to three main things. One of them is that the SPH that we are measuring depends on the inclination angle of the stars. So if the star is inclined, we will see more or less the active regions. Then it also depends on when during the cycle of the star we are observing we're having the observations. So that's the second point. And the third point is there is also a dispersion due to the metallicity of the stars because we have a broad range of metallicity. So this is just a reminder of what was seen in other magnetic proxy, where you also have this saturation and this unsaturated regime, also for fully convective stars, which are the colored points. So this is an X-ray luminosity. You also have the same thing for magnetic field. It was also seen in flares observed by Kepler. So this is divided into spectral types, and you can see that for the D and F type stars, this relationship not to hold that much. So I think that's something interesting going on here. Another quantity that you can also, where we have seen a similar behavior is what we call the mid-frequency continuum. This is the work that we did with Tim Brown this year, where we analyzed a sample of Sunlike stars from the Pleiades and also from field stars observed by Kepler. And so here you can see the power spectrum density of these stars as a function of frequency. So for the Sun and a couple of K2 targets. And basically we are measuring the mid-frequency continuum is the average power between 20 and 280 microhertz here. And we were not sure if that was what we were measuring was related to convection, magnetism of the stars. So here you have this frequency continuum as a function of the Rossby number, and seeing that we have a similar behavior to the magnetic proxy, we concluded that this quantity is linked to magnetism, though we don't understand exactly what it's representing. So let me come back a little bit to saturation. So there were different explanations that were given to explain this saturation for the low Rossby number stars, either saturation of the dynamo or saturation of the filling factor of the active regions, or also centrifugal stripping of the corona for fast rotators. So this is still quite an open question, and I think we can have more discussion here. Then there is this interesting dip that I mentioned earlier. Different theories have been put out on this. Yeah.
Sorry, quick clarifying question. Why is it Rossby model over Rossby sun? What does it mean that you're normalizing versus Rossby sun? From Pascal Gaffo.
Yeah, it's just for understanding where the sun would be. So, it's just a normalization factor. Yeah. Okay, so yeah, different theories have been put out for the explanation of this this dip. Either it's just an observational thing where it's a cancellation effect between active regions and faculae. Another explanation is the relation with the rotation gap that we can also see here when you look at the rotation period as a function of effective temperature. This is also something Jim mentioned about the stalling of the magnetic braking. So you can see that you have this gap, this bimodality in the rotation period, mostly for the KNN stars. And McQuillan has suggested that this bimodality could be related to two bursts of star formation, but since this gap is also seen in the K2 fields, which are different regions in the galaxy, this seems to be less likely to be the case. So coming back to this gap, there is also this theory about what Jim also said, that it can be explained by the core envelope coupling that's happening at these young ages for the stars. And so maybe that coupling can impact the magnetic activity and creating lower activity for those targets. Okay, so here I divided the SPH Rossby plots into spectral types. Again, in F dwarfs, T dwarfs, K dwarfs. Well, we don't have many F dwarfs here, so I will not talk about them. But you can see that for the F dwarfs, we don't really see this the dip here. It seems to have kind of a saturation, but it seems that the F dwarfs are in a regime where they are basically less active than the target, the spectral types. We can also see that the magnetic activity level is decreasing when you are, increasing when you go to K dwarfs. And there is maybe some hints about the slope that seems to be a little bit different for different spectral types. So now I just wanted to focus on Sunlike Stars to see how the Sun compares to stars very similar to the Sun in terms of effective temperature, metallicity. So we do a cut very close to the solar values using spectroscopic data. And so you have the SPH again against the Rossby model normalized to the solar Rossby. And the red points here are the value of the SPH for the Sun between minimum and maximum activity. And basically, you can see here that the sun seems to be very comparable to stars with a similar Rossby number. But you should still remember that there is a detection bias of the rotation period, and this is only based on stars where we managed to measure rotation period. And we know that the majority of the stars from Kepler, we didn't manage to detect rotation period, and we did some simulations of like final of the sun, showing that in many cases the sun was in the non-detected rotation period, so the sun wouldn't belong to this sample in many cases. That's another work that is being done by Angela Santos, where we're studying the variability of the SPH. So we're looking at the standard deviation of the SPH here. This is something that was also seen with calorimetric observations, I think. So basically, you can see a nice correlation between the sigma SPH and the mean value of the magnetic activity level of the stars. So you have the M dwarfs, and K dwarfs, T dwarfs, and F dwarfs. And in blue, you can see, not in green, sorry, you can see the sun that seems to be in the same regime as Sunlike Stars. Okay, so one of the last point I wanted to show you is about trying to derive this SPH relationship. It's something that we can do. That was the main objective of this work. So we, again, we selected stars similar to the sun in terms of effective temperature. The ages are coming from the models. And you can see how with the age of the star, the SPH is decreasing. And we could imagine that maybe in this regime between 1 and 4 gigayear, if we measure an SPH value, we can have a measure of the age of the star with 20–30% uncertainty. It's not the best, but still something we could use. One last point that I will go through very quickly is, since we're measuring active regions coming in and out of sight of the visible disk, we can try to look for the lifetimes of these active regions. So in the past, Giles and collaborators were using the ear-folding time of the ACF, and we showed by doing some very simple simulations that the ear-folding time, which is the blue points here, as a function of the input lifetime of the active regions, is in general underestimating the real lifetime of the active regions. Whereas now we are using the linear decay of the ACF, which are the red points here, and it seems to be more reliable, but for a longer active lifetime of active region, we still start to underestimate the input values, and this is very biased on the length of the observations that we have. Okay, so for the conclusions, we've seen that we have measurements of magnetic activity and rotation period for large sample of stars. We still, by comparing the sun to solar analogs, it seems to be similar, but we need to be careful about the detection bias. We still need to have more spectroscopic data to refine the relationships, and TESS and data will probably provide more insight into this. And I just wanted to finish with questions for you. You can still ask me questions, but these are points that I would like to discuss with all of you to understand what we are observing for the F stars, the situation, the dip, and we'll stop here. So thank you.
Thank you very much. Do we have any questions from the live audience or the Zoom?
Hi, Savita. Jamie Tyar. Do you have? So I didn't see any evidence for supersaturation in any of your plots. Do you think that's a function of the metric you're using, the sorts of stars that you looked at, or do you not think supersaturation exists?
Yeah, I'm not sure if we can see it in our proxy of magnetic activity, because I think it was seen in the X-ray luminosity, right? So since we are really probing the photosphere, maybe it's a phenomena that's happening at different region of the the star's atmosphere.
Hi, Savita. Evan Anders. Thanks for the great talk. I have a question about the observational bias, because I am not good at observations or ever do them. So why don't we have observation rates for most of the Kepler stars? And if we could, like, is this something that you think would affect this data, or is it something you're not worried about?
Okay, so the detection bias, well, there are several aspects that will affect how we are measuring the rotation periods. So first of all, maybe during the 4 years, the star was in a Maunder minimum, and we're not observing any spots, and we can't detect any rotation periods. The inclination angle is the other reason, maybe, because if we are pole on and all the active regions are on the near the equator, then we will not see any modulation. Signal to noise ratio is the other reason, maybe in some cases where you have less contrast between the spots and the rest of the star. So yeah, I mean, and for the sun, so what we did and what Reinhold did was to take, so we did take Virgo data where we have photometric data observations for 25 years, and took 4-year subseries to mimic what we have with Kepler. And depending on when we are in the cycle of the star, sometimes we just don't detect the rotation period. So, and that's why it's a bit concerning, because maybe many of the stars that we're observing are not detected because they are like the sun, and the stars that we're observing are not like the sun. So, yeah. Yeah.
Daniel Quene, Pascal and I actually have the exact same question, follow up from Jamie's question. What is supersaturation?
Okay, I don't remember exactly, so maybe Jamie, you can it's.
Oh, sorry.
Okay.
So, Jamie Tyre. So sometimes when you see plots like Savita was showing, where you have kind of that, as you go to lower Rossby number, the proxy for magnetic activity goes up, then it flattens. Sometimes on the other side of that flattening, you will see a downturn. This is mostly in the X-ray data, but it's usually only a couple of points. And so there's been an argument, are those points just a few weird points that they measured wrong? Is there a real second regime where, you know, you're rotating so quickly, you've centrifugally stripped off interesting stuff and you can't magnetic field anymore? Is there something cool going on with the corona or the chromosphere or something like that? But it is not seen in every proxy. It is not seen in every data set, and it is theoretically complicated to explain. So it's always interesting when you see a new measurement, like, do you have any supersaturation? Do you believe any supersaturation? If you don't, are you confident there's no supersaturation? So that was kind of why Savita was answering the question.
Hi, Savita. Vicky Antochi here. Thanks for the nice talk, and I apologize if you said it and I missed it. But do you have an additional bias from observing bright and dark regions at the same time that will cancel out? I think you might have mentioned that, right? Is there a way to estimate that?
There is a way to estimate. I'm not sure. But so basically, with the way we are doing the measurement of the SPH and the rotation period, we're looking really at decrease of the brightness and increase. And I think that's, in that way, we are more sensitive to spots and active regions rather than having faculae, because this is happening on a more global scale, and this is something that I think we are less sensitive to that. So,
Can I ask a follow-up quick question? Do you have any estimate on for any of the stars on where the spots are located on the surface? Is it rather along the equator or more towards the pole?
Well, with this, what I showed you, not really, but there are some studies where Angela Santos, for instance, was looking at the high peak ratio. So you have harmonics of the rotation period, and you look at the ratio of the amplitude of the main periodicity and the harmonics, and this can give some insight on where the spots are, but it's very complicated because it's not valid for all the configurations. It's better if you already know a little bit the inclination angle of the star, and it works better if you have less spots than too many spots.
Do we have any other last questions? We're just about at time. Okay.
Another question from Pascal Garot about supersaturation. Could the supersaturation have to do with the size of the convection zone rather than rotation rate? For instance, you could imagine stars with thinner convection zones could have low Rossby numbers, but maybe not enough of a convection zone to generate much field.
Yeah, that's a good question. Maybe. I don't know.
So in particular, is there like a mass dependence, which I think would say something about the size of the convection zone?
Yes, yeah. I'm not sure anyone has really looked at this, but maybe that's something we could have a look with our data, and like not only look at general F and G type stars, but focusing on smaller ranges of masses and see if we can pin down where that's happening, if that's happening.
Van Stadius, I can just comment on that real quick. In addition to what Savita said, is that I think the problem is in the thin convection zone cases, most of the time you don't detect it in any of the proxies because it is quiet. And so I think most of these things where you see super saturation, you're looking at like really big convection zones and like M-Dwarfy type things.
Do we have any final questions? If not, let's thank our speaker once more. And I believe there's coffee and